Welcome back to Finite Element Methods. This is class number 6 for this course at the University of Tennessee, Math 574. We're talking about Sobolev embeddings because we're going to need these for analyzing some aspects of our finite element methods, in particular the convergence properties and the error estimates for our finite element methods. We were talking about the Sobolev embedding theorems where we're first just looking at the continuous embeddings. After this, we'll get on to the compact embeddings. But before we do that, I wanted to go through a number of examples to show you what's going on in this case. All right, so let's do a couple of those. And we started off with this one. We finished with this one last time, but I said at the very end, there's some interpretation to do here, and I want to go into depth on that interpretation in this example. So we're looking at the case where D is equal to 1, so one dimension. K is greater than or equal to 1, so that means that the number of derivatives in this space in the KP spaces is going to be 1 or 2 or higher. And P, the value of our LP spaces, it should be strictly greater than 1. So for example, a common one here would be P equals 2. Although you can have any real numbered values for P between 1 and infinity. In this case, not including 1 or infinity. So in this case, the product of K and P is strictly greater than D. So this means we're above the critical case. And this means that the functions of our Sobolev space are actually quite smooth. In fact, they're continuous functions. We'll go into more depth in this in just a moment. But in this case, we're in that last case, case 3, where K and P are large enough so that WKP embeds into the continuous functions. What this means is that the KP space of an interval, in this case, we're considering a finite interval because we're interested in the case where the set is open bounded and has a Lipschitz boundary. And in one dimension, it suffices just to consider a very simple interval. Now, we know that, or what this theorem tells us is that the KP space for this interval is a subspace of the continuous functions. So if I pick out a function in here, it must also be, this is my crude Venn diagram here. If I pick out a function from this space, it must be in this space. And furthermore, that embedding mapping is a continuous mapping in the sense that we had, as one of you were asking, an estimate which looks like this. Got a little bit crammed there. So that should be my KP. So sometimes, by the way, instead, to save a little bit of writing, instead of writing WKP, I'm just going to shorten that. It's fairly common convention, and just write that as KP, if it's understood what I'm talking about. So that's what I'm doing here. This is the usual KP norm, the usual Sobolev norm on this side. So we have this as a subset of the continuous functions, and we have this estimate for remember the linear embedding operator, which in this case is just the identity. Now, this is a bit puzzling, and it takes a little bit of creativity to understand because normally functions that are in the Sobolev spaces should be interpreted in the same way as LP functions. In other words, if we redefine the points of a function from that space on a set of measure 0, it doesn't change that function essentially. It doesn't change it really in any way. And this is still true in this case. So how could a function which looks like this function in red, which turns out to be an H1 function, how could this function be understood as being continuous? Okay, a C0 function on the closed interval from A to B. Well, the interpretation here that is required is that you can think about these functions in the way we normally do in measure theory as an equivalence class of functions. So we think about all the functions of this class being the same as long as they differ only on a set of measure 0. And what this means is that if I say that this h1 function is actually C0, what that means is there's a member of the equivalence class of functions that is continuous on the closed interval from A to B. So I hope everyone appreciates that distinction. It means that these are really equivalence classes of functions, and every function in the equivalence class is exactly the same, except they differ on a set of measures 0. And what I'm saying is, within that equivalence class, there is a function that is continuous. So sometimes we call that the continuous representative of the function class, or the equivalence class. So this is still true that functions from this space, these Sobolev spaces, are like LP spaces, or like functions from LP spaces more generally. So in this case, this function here, even though it's h1, is not continuous because its point, or, well, I don't know what this value is here at this point x, say. At this particular point, well, let's call it x naught. At this point x naught, the function that I've shown here is definitely discontinuous. But it's easy enough to see that I could fix this function up by redefining that value at x naught to be the continuous value. And so this is how we interpret this result, that these are inside the space of continuous functions. They're a subset of them. And that works because we can redefine functions from this equivalence class on a set of measure 0, and we can find in that equivalence class a representative which is continuous. Okay, so that's an important point for you all to keep in mind. Let's do a couple more examples to see what's going on here. So suppose k is equal to 2, p is equal to 2, and d is equal to 1. So again, we're in one dimension. We're looking at the Hilbertian type Sobolev spaces, for which whenever p is equal to 2, we switch to the notation h rather than w. In this case, k times p is 4, right? 2 times 2, and that's strictly greater than 1. Again, we're back in the third case, and in this case, I'm going to do this in much more detail. So our theorem tells us that h2 continuously embeds into this function class CLB over the closed interval a to b. Oftentimes, I'm going to go ahead and drop this beta because this guy also continuously embeds in CL without the beta. It's very straightforward to show that. So oftentimes I'll drop the so-called Holder exponent, but you don't need to, of course. It's just oftentimes you don't need it. Now, what is our theorem telling us that these values for L and B are? Well, L by the formula is going to be K. Remember, K times P is strictly greater than D. So we're going to have K minus D over P. K is actually bigger than this fraction. This is the largest integer, the largest integer, which is less than or equal to D over P. And I'll get to that exact calculation in a moment. And then, of course, you subtract 1. That's what the formula tells us. That's what the theorem tells us. So K is equal to 2. D over P is equal to a half. The largest integer less than or equal to a half is just 0. So we do 2 minus 0 minus 1, and that, of course, just gives us 1. So that's what L is. L is 1. And what is beta? According to our theory, that tells us that it's the largest integer less than or equal to D over P plus 1 minus D over P. So this means, so what happens when I take this minus that? It means you get a number which is between 1 and 0, but then we're going to add 1 to it, and that gives us a number between 0 and 1. What number do we get in this case? We get precisely equal to a half. So this is the so-called Holder exponent. So if you've never studied Holder spaces before, it's not a huge deal because it's not so important for us in this class. But give it a Google and see what it means, what these Holder continuous spaces mean. If you another way you can find out what these are and what they look like is to go to the Atkinson and Hahn reference, and it gives a nice detailed explanation of those spaces. But as I said, we can drop the Holder exponent because this space with any Holder exponent is always going to continuously embed into C1. That is the space where we've dropped that. Okay, so that's what I'm usually going to do. So this says that H2 continuously embeds into C1. So this says that these functions, H2 functions, are actually C1 functions. They're fairly smooth functions. Okay? Well, of course, these functions can be redefined on a set of measures 0. And so these are equivalence classes of functions. And what this result means is that in this set of equivalence class, or in this equivalence class, there is a C1 function which represents all the other functions. That's what, or how I should say, you interpret that result. Okay, let's do another example. Suppose that D is anything between 1 and 3, P is equal to 2, and K is equal to 2. Then this says that the theorem tells us that W22, which is the same as H2, remember, because anytime we have P equals 2, we're just going to rewrite this as H, H to the K power. H2 continuously beds into C0. This is an important result for us in finite element methods because it always says that if we have H2 functions in any one of the relevant cases that we're interested in, we're mostly going to be interested in physical problems. And so physical problems have dimensions which are between 1 and 3, depending on the physical application. Then this is always going to tell us if we have an H2 function, then those are continuous functions, and we can always sample with there's a representer from that equivalence class of function which is continuous, so we can always meaningfully talk about the point values of the functions in this class. Okay, so again, that's very important for us for finite element methods. Let's do another example. Suppose that K is equal to 1. So that means spaces with one weak derivative. P is equal to 2 and D is equal to 3. This is a very important example. So this is a subcritical case. Subcritical because K times P is strictly less than D, or in other words, K is strictly less than D over P. K in this case is 1. D over P is, of course, 3 over 2 because D is equal to 3 and P is equal to 2, which is exactly the same as saying, it's the same case as saying that KP is strictly less than D, or 2 is less than 3. So in this case, our theorem tells us that WKP, P is equal to 2 in this case, so we'll replace the this space just by H1. It's got one weak derivative. These are functions with one weak derivative. This space always continuously embeds into LQ for all Q between 1 and 6. So I should actually add that. The reason why it's between 1 is, well, 1 is the smallest that value of Q can be and still be meaningful. So any Q between 1 and 6, we get this embedding. So this says that actually H1 functions, oops, didn't mean to do that, meant to do that. H1 functions are not necessarily continuous functions, okay? But they are from this higher LP space, L6. So this space here is based on L2 functions, right? It's saying spaces with spaces that are functions that are weakly differentiable such that the function and its derivative are in L2. Well, what this is saying is that the function itself is actually in a space with a higher uh, Lebesgue exponent, namely up to 6. So this is telling us something nice, even though it's in that subcritical case. It's saying that all the functions of this space are actually in L6. And of course, we also know that we have this estimate, right? So there's some constant such that the H1 norm of V is dominates in some sense. Well, you have to multiply by a constant, but it dominates this norm. Okay, so there exists some constant, not necessarily unique, right? Because if I can find one constant, then that constant plus one still works for all V in H1. Okay, so there's two parts to continuous embedding. There is the fact that the functions live inside this space, and we also have the continuity of the embedding operator. The embedding operator, that's right. Let's do another case. So hopefully you're starting to get the hang of these. Um, this turns out to be what we call the critical case whenever k times p is equal to d. So suppose that k is 1, p is 2. So again, we're back in the Hilbert-Sobolev space, Hilbertian-Sobolev space case. K is equal to 1, so that we have one weak derivative. D is equal to 2, so that's the number of space dimensions. In this case, k is actually exactly equal to d over p, or in other words, k times p is exactly equal to d. 2 is equal to 2. Either way, we get the same result. WKP, which is in this case, I think I forgot to rewrite it. So this is precisely just HK, right? And so HK continuously beds into LQ, but there's no upper limit on LQ. So Q can go all the way up to infinity, but not quite exactly equal to infinity. This has important consequences. So if it could go all the way up to L infinity, that says that those functions are actually bounded. It says that their essential supremum is bounded, okay, which is an important distinction. It says essentially, that the function is bounded. It's a bounded function, not necessarily continuous. Now, these functions are not bounded because we don't go all the way up to the q equals infinity case. We're not quite there, but as large a q as you want to get, you're going to have the functions from this space are going to be in that space. And that's a very important point because these spaces can be almost quite as nice as L infinity. Almost, but not quite. So we don't get to go all the way up to L infinity with the essentially bounded functions. We're, we're within epsilon, if you'd like to think about it that way, of getting there. Now, of course, that's the so-called critical case. If we're above the critical case, then every time you're above the critical case, you have a continuous function, or your functions are actually continuous on a closed interval. But what do we know about that, or a closed set? We know that continuous functions defined over closed or compact sets, in fact, because this could be in higher dimensions, in compact sets are actually right. Continuous functions over compact sets attain the max and min, their max and min. So these functions are always bounded. That's a very important point about those functions. So they're not just continuous, but they're also bounded. Now, if we're in the critical case, critical is whenever kp is equal to d, we don't quite get there to boundedness. right? A function out of this class might be bounded, but we can't say that that's true generically. All right, so here's the other theorem that we were alluding to earlier. So that is whenever we have the so-called compact embeddings. Interestingly, the results are really almost exactly the same. All right, so with the same hypothesis, instead of just knowing that this is a continuous embedding into LQ, we can actually show that it's a compact embedding. So that's one extra feature. A compact embedding says that you have the containedness property. So in other words, you have the subset property. And you also have the continuity of the embedding map, but you have one extra property, and that is you have the compactness of the embedding map. And really, it's hard for new students who are learning this concept for the very first time to appreciate how powerful compact embeddings or compact operators are. It turns out that they're extremely, extremely important for a lot of stuff we do in not just differential equations, but in applied math more generally. And the best thing I can do or say right now is that we're going to get to some applications where I show you exactly what that means. All right, so don't worry so much if you've never heard of compact operators or compact embeddings before. Just remember this for now. First of all, a compact operator is a continuous operator plus this extra little important piece of information about subsequences. And we'll talk about an example of that in a moment. And also, um, it is a little bit of a confusing concept. So don't worry about what it all means now because we're going to when the times come when it's important, I'll make sure to emphasize them. Okay. So 1 and 2 are exactly the same as for the continuous embedding case. All that we're doing is really adding that extra arrow and saying that these embeddings are also compact. The only difference comes for case number 3, and this part of the formula is still the same. It's this part here is a little bit different. This part here is a little bit different. And so I'm not going to harp on that or what it means again. It's not so important for us because that's just the Holder exponent, and we usually drop that anyway. But let me give you a couple of examples what's going on here. Okay, so these are all more or less the same as the continuous embedding cases. It's just we get this extra information about compact embeddings almost completely for free. Suppose we're in dimension 3, k is again equal to 1, p is equal to 2. So we're again in the case where we're subcritical. K times p is less than d. 2 is less than 3. So here it says the same thing it did previously, except that we get this compact part for free. H1 functions are compactly embedded into LQ for Q between 1 and 6. So what this means is we have the continuous embedding, but we also have the compact embedding as well. So what is so you remember what the continuous embedding you remember what the continuous embedding part means. Let's talk about the new part, the compact embedding. So suppose that I have a sequence from H1. Okay, so here's the containment of our spaces. We've got H1 here, and we've got LQ out here. So these functions are actually in LQ. They're contained inside. This is my Venn diagram for LQ. Of course, it's an infinite dimensional space, so drawing it as a box isn't really fair, but you get the idea. Okay, so now suppose that I have a sequence in here. Okay, sequence just means it's a bunch of points moving around in that little set, indexed by n. And let's suppose that it's a bounded set. Okay, so bounded bounded sequence. So a bounded sequence means that for there is some m such that for all indices n, Vn in H1 norm is less than m. That's what it means to be a bounded sequence in H1. If you replace this by H2, then the norm here is going to be the H2 norm. Okay, and boundedness means the same thing. So what does it mean to be compactly embedded? It means that we're continuously embedded, plus we have this extra little subsequence bit. And the extra little subsequence bit is this. There exists a subsequence of the original sequence and a point V in LQ such that the subsequence converges to the point V. In other words, in the LQ norm, the value of the subsequence minus the value of the limit point in that norm converges to 0 as k goes to infinity, right? So that's exactly the same as saying that V n k converges to V. Sometimes I'll write it like this, or actually in LQ. So when I write LQ above here, that means that that convergence is in that norm. Okay, so that's another way of writing exactly that fact. So that's the extra little bit. Why is that so important? And why is it important for our applications? Well, I can only answer that question when I come to the appropriate application, which we will do in a bit. Okay, so put that in your pocket. You have this extra little bit of information, which I claim is going to be useful for us. Let's move on to another topic. What about boundary values for functions that are in these Sobolev spaces? So if I ask you what's the boundary value of a function like this, which comes from this Sobolev space H1, you should complain a little bit. Because remember, I told you up above that these functions come from a function class where we can rearrange the values of these points on a set of measure 0 without changing them or without leaving the equivalence class. Well, we explained earlier that there's some member of that equivalence class which is continuous on the closed interval from A to B. So if I have a member from this class, I can immediately tell you what its expected boundary values should be, even though in truth, I could reimagine the value, say, at B or A, the boundaries, by changing its value to say something up here. And I wouldn't change that. I wouldn't change the nature of that function in any essential way in the function class. But this containment, what that means is that, again, there's a member of the equivalence class which is ultimately a continuous function. So boundary values, or if I want values at any point in space, makes sense. Okay, again, boundary values, and in fact, at any point in space or any point in the domain of definition for the function AB, then the values at that point make sense. It makes sense to ask what are the values at a particular point. So here's my general question. How can we get boundary values from a function whose values at certain points in a set of measure 0 can be changed? And the answer is you have to look at the member of that equivalence class which is known to be continuous. And then you can then you can have point values for a continuous function. Every continuous function has well-defined point values, okay? Now, otherwise, we have to do something a bit special. And the special thing here that we're going to do is we're going to introduce, well, we're going to state a theorem. And in stating the theorem, we're introduced to this operator called the trace operator. Trace operators help us understand how functions in Sobolev spaces can have boundary values. Suppose that omega is in RD is an open bounded domain with a Lipschitz boundary, which we're going to call gamma, capital gamma. Okay, so this is my notation for the boundary, and we're calling the boundary we're giving it another symbol, shorter symbol, gamma, capital gamma. For any p between 1 and infinity, not including infinity, there is a continuous linear operator, gamma, which takes W1p functions and it assigns it or pushes it to a function in this class, LP over the boundary. So this is a standard LP space, but it's defined over a boundary. And notice that if we're in d dimensions for omega, the boundary has one space dimension less. Okay, we can think about it like this. Suppose that we're in two space dimensions. If I'm in two space dimensions, then this might be my omega. My boundary for omega is what I'm calling gamma, capital gamma. So the boundary always has what's called codimension 1. That means it's one dimension smaller in essence than the set that it bounds. So the boundary is essentially a one-dimensional set, whereas omega is a two-dimensional set. Okay, does everyone get the distinction there? Now, I can think about functions defined on the boundary. Okay, so these would be functions defined on this essentially one-dimensional set that we're calling omega. So I can make LP functions on that space. I could make L2 functions on that space. I could think about Sobolev functions on that physical boundary. So what I'm saying with this operator is it's taking functions which are defined on omega. These are Sobolev functions defined over omega, and it's mapping them into LP functions defined on the boundary. So how is this possible? Well, it's possible because I have a derivative here, and that derivative is giving us some smoothness information about the function, and it's saying it's smooth enough so that I can expect to be able to find functions on the boundary or I can expect to have some notion of boundary values, and that boundary value is a function in one space, in one dimension lower, in this space LP. Okay, now it has three properties which are very important. The first one, and this is kind of the most important, is the boundary trace is just exactly equal to the value of the function, okay, if V is already continuous over the closed set omega bar. Okay, so this is a compact set, right? Because it's a bounded set. It's now known to be closed in RD. So continuous functions over those compact sets are bounded functions, and they have well-defined values. So if that function is actually continuous from the beginning, then the boundary trace is going to give you nothing more and nothing less than the value of that function restricted to the boundary. I should say it like this. It's just the function restricted to the boundary. Okay? That's good because that tells you it repeats it's going to generalize the notion of what we already think of as boundary values. But it goes a little bit further. If it's not continuous, but we know that it's only W1P, then we know that there's going to be some function which lives in that space that gets mapped to by this function gamma. Okay, and we know that that gamma map has to be a continuous linear operator. Now, it's kind of like an embedding operator, but it's not exactly. Embedding operators, you could argue that the mapping itself is just the identity map. In this case, it's not the identity map because think about it. If that were the identity map, then it would map V to itself within W1P, and that's a function over this set omega. But what we really want is its values on a boundary. So in this case, this is not an embedding map. Okay, so this is not an embedding anymore. It's actually something a little bit different. In any case, that mapping gamma is a continuous mapping. And by continuous mapping, we just mean it's it's also known to be linear. And so this is just the statement essentially of what it means to be a continuous mapping. The linearity is an extra little bit. Okay, so this is by definition what it means for an operator to be continuous. If I measure the value of this is kind of the this is the value of V under this map gamma. So this is of course in this space LP gamma. So I can ask what is its norm in that space, or what is its norm in the LP norm. That has to be less than a constant, some known constant, times the norm of the function in the Sobolev space norm. And remember, in this case, now we're talking about this as a function over that whole set omega, right? So the distinction is omega is this big set and gamma is its boundary. And of course, we know that gamma has codimension 1. It's, in terms of dimensions, a little bit smaller. Well, it's 1 dimension smaller, right? I hope everyone can see that. In this example, omega is a 2-dimensional set, but gamma is a 1-dimensional set, essentially. All right, so that has to be a continuous operator. And finally, it also has to be a compact operator. So in case you've never seen the definition of a compact operator, here's what it means. For any bounded sequence in W1P, okay, so that's the domain of the operator, there is a subsequence of that such that, well, a subsequence and a point in LP such that, so if I look at this sequence under this mapping omega, then it's in not the domain anymore, but the range. So this target has to also be in the range as well. And what we're saying with a compact operator is that the values of the sequence in the images of the sequence in the range converge to some point in the range in the topology of the range space. Okay, so this is the topology of the range space LP. So this, all we're saying basically then is that this mapping agrees with our notion of what it means to be boundary values whenever the function is continuous. There's the boundary values. It is continuous. It's a continuous mapping, and it's also a compact mapping. That's it. Okay. So that's the so-called boundary trace. Now, the nice thing about boundary traces is that it works for functions which are not known to be necessarily continuous. Okay. It works for functions which are not necessarily continuous functions, and that's a nice thing. So this operator, gamma, whose existence is guaranteed by the last theorem, is called the trace operator. So we'll talk a lot about trace operators, but it's basically going to fade into the background, and it won't be very important because you'll never think about it. It'll be important, and we'll emphasize it from time to time, but it's probably going to fade from your memory because you're just going to think, oh yeah, so H2 functions in this setting definitely have a trace operator. Okay, so the trace operator tells me that boundary values for functions in this class make sense. Okay. All right, so the last topic that I want to talk, well, there's kind of two topics. Integration by parts, and then an important one on the Poincare inequality, which is not closely related, but somewhat related, I guess. We're going to be using facts that we know about functions that are continuous or smooth, and then we're going to use what are called density arguments to prove that they hold true for these functions from Sobolev spaces. So here's what I mean. Suppose that we have a boundary or a set that is an open bounded domain, but it has a fairly nice boundary, a Lipschitz boundary. So this means it can have corners on it, but it can't have radically bad corners, okay? Um, if you don't like thinking about sets with corners on them, just think of, for now, it's an open bounded set with a really smooth boundary. Open bounded set with a nice boundary. The boundary we're going to again call gamma. For almost every point on gamma, there's an outward pointing unit normal vector that is perpendicular to the boundary curve. So the only place where this is not true is suppose that we have a boundary curve which looks like this. Okay, so this is not a bad cusp or anything like that. So there's our boundary curve. Looks like that. Well, and then it goes off. So here, let's see, tilt my iPad a little bit. We have unit normals for this boundary pretty much everywhere, right? Except it turns out for Lipschitz boundary, it's a nice boundary, but it's kind of like um, it's 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 like the minimal nice boundary that you could possibly have. It has some problems with it, but they can be overcome. The problem with these types of boundaries is they can have corners to them. And so at a corner point, you might not have a well-defined outward pointing unit normal. So precisely where do we have problems? We have a problem right here where the boundary fails to be smooth. At that point, we don't have an outward pointing unit normal. What, you know, what normal vector, that is, what unit vector can I ascribe to that point such that it's going to be perpendicular to the boundary at that point, the boundary curve? The answer is there aren't any. But the nice thing about Lipschitz boundaries is that for almost every point on the boundary in the measure theoretic sense, I can find unit normals that are unit normals in the traditional sense. Now, if this was what we call a C1 boundary or a C2 boundary, then definitely no problem ever of finding a unique unit normal, outward pointing unit normal at a point on the boundary curve. Okay. Actually, I should say I need to probably rethink this term here, curve, because we could be in hyperdimensions, right? So if D is 100, this is still true. It's just that the boundary is now a 99 dimensional space. So I wouldn't call it a boundary curve anymore. I would call it a boundary, uh, uh, a codimension one set. In any case, I'll fix that up when I post them to Canvas. Repost, I guess. And by the way, I usually try, and I was able to succeed in this case of getting the notes up on Canvas before the start of class. So I'll try to do that as often as I can. And for those of you who have access to the notes on Canvas, you can get them uh, before class starts and follow along. All right, so that's one thing. And furthermore, for all u and v in C1 omega bar, so these are functions that are fairly nice. They're C1 functions over this compact set omega bar. So they're definitely continuous functions. They have a classical derivative, which is also continuous. And of course, they have to be bounded. Then for any j in the indices between 1 and d, inclusive, I have the usual integration by parts formula. So that says that if I integrate the partial derivative of u with respect to xj times v over the domain, then I can move this derivative from the u onto the v. I incur minus sign when I do that, and I also gain a boundary term when I do that. The boundary term has, uh, well, what is the form of the boundary term? Well, it has no derivative on u or v, and it has a component of the normal vector in the jth direction. Remember, we said this guy is defined almost everywhere. That's good enough to do an integration if it's defined almost everywhere. This is my boundary integral term. J, this nj here is the jth component of my outward pointing unit normal, which exists almost everywhere. This is a classically known theorem. In fact, it's usually proven for boundaries which are smoother than Lipschitz continuous boundaries. And then, so you can prove them for a C1 boundary or a square. And then what you do is after that, you prove them for more complicated or open bounded sets with more complicated boundaries. So we're going to take this as being a known fact, and we're going to try to establish this for functions that are not so nice as this. So what do I mean by that? Well, I mean the next theorem. Suppose that, again, omega is all the same. It's an open bounded set with a Lipschitz boundary. So this means a fairly nice boundary. Then the same formula holds, but with these functions here, which are not classically differentiable functions, u and v and h1, right? So these are not C1 functions. These could be rough functions. The formula, notice, is exactly the same. It's exactly the same. Notice that everything makes sense in sight. This is going to be a weak derivative now, right? So this means that this will be a function in L2. This is also a function in H1, so it's definitely in L2. I can integrate the product of two L2 functions that, that's what the Cauchy-Schwarz inequality says. It says that if I multiply two L2 functions together, then the product is L1, and I can get the integral. What about these functions here? Everything here is going to make sense in sight. And the reason is because the trace operator says each one of these are going to be L2 functions. The only difference is, well, what happens to this guy? We'll talk about that in a moment. This is an H1 function. This is an L2 function. So the product is definitely an L2. So this makes sense as an integral. Everything makes sense, but we have to prove that this formula really does hold. Well, I didn't talk about this subcase, but it's not too hard to show that C1 is dense in H1 and dense with respect to the H1 norm. It's possible to show this. What does it mean to be dense? It means that if I have points like U and V in that space, then I can find sequences from the dense set that converge to the points in H1, and they converge in the manner or in the topology of H1. That means in the norm of H1. So I have this type of convergences. So it doesn't matter how or what U and V I pick from H1, I can always find a function which is getting arbitrarily close to it. And by doing that, I can generate these sequences which converge. Now, each one of these sequence or members of these sequence are in C1, right? And since they're in C1 and the boundary is Lipschitz, we know that by the classical integration by parts formula, that this holds for un and vn, okay? But now what I want to do is I want to take the limit of these integrals as n goes to infinity and show that the limit of these is precisely going to be the derivative of u here and v here and the integral otherwise. And likewise, I want to show that these limits are also exactly the limits that you would expect. If I take the limit as n goes to infinity, I'm just going to get the integral of u and v against n. So let's see, how does this work? Let's start with this guy here. I want to show that the limit of that integral is precisely this integral over here. See, there's no n's on u or v. So I'm just going to compare the two. And I'm going to put their difference in absolute value. Then I'm going to add 0. So investigate this term right here. Notice that it's exactly the same. Let's see, is that true? No, sorry, I made a mistake. I'm adding 0 here. Okay. I'm adding 0 because I just do a quantity minus the same quantity. And this term were the terms that were already in the absolute value. So I have a quality here. Now let's group some terms together in a sophisticated way. I want to compare this term with this term. Okay. No, sorry. It's this term and that term because I want the minus. And then I want to take this one and compare them. So what I get when I compare these two terms is, well, they have almost the same integrand, right? This term and this term are the same, but this one, I keep screwing this up. Sorry. Which ones am I taking here? V and Vn. So it's these two, right? No. Okay. Let me back up here. It is these two. There we go. I'll get it right one of these days. And what I did was I swapped the sign. Okay, so these two, and the reason is because I want this term to be the same, but these two terms to be different. Okay, so I think I have it. These two terms combine to give me that one. And then I'm going to look at these two terms. They should have the same and then the difference. Okay, same and then the difference. Yes, okay. So I'm comparing these two and then these two. They have to have opposite signs. Okay, and then I'm going to use the triangle inequality. And that looks correct now. Now I'm going to use the Cauchy-Schwarz inequality. So what does Cauchy-Schwarz say? Cauchy-Schwarz says that this integral is less than the norm of that integrand times the norm of that, okay? Or that part of the integrand. So that's just the L2 norm of du dn dxj. And this one is going to be v minus vn in L2 norm. Likewise with this one is going to be that L2 norm there and this L2 norm. Okay, now what do I know about this guy here? Well, we said that UN is a sequence that converges in H1. So it has to, every convergent sequence has to be a bounded sequence in the same norm. Well, this doesn't look like the same norm, but notice that it's the derivative in the L2 norm. I can bound that by the H1 norm of UN. And then I know that has to be a bounded sequence. All right. What else? This is just a fixed number, but it's the L2 norm. I'm going to beef that up by making that an H1 norm. So, by the way, for any function that's in H1, if I look at the L2 norm, that's always beat by the H1 norm. Why? Well, because this kind of has the L2 norm already built into it. This H1 norm has L2 as part of it. So this always is the case. Okay, I always can dominate as long as F is in H1 to begin with, then I can always use that. Likewise, if I know that F is in H1, let me expand this out a little bit. I can also say something else. I can also say that it's any of its derivatives, any of its weak derivatives, also is going to get dominated by the H1 norm for the same reason. Okay, because this norm is kind of already in that norm. Plus it has some extra stuff in there. Okay, so that's why I've been able to replace that with an H1 norm. This guy gets replaced with an H1 norm. They all do, in fact. Now at that point, I can use the fact that I know that this is a bounded sequence. All right, this is a fixed number. So these guys go to 0, right? Because I know that Vn converges to V and Un converges to U. That's all I need to know. So this goes to 0, That term goes to 0. So by the squeeze theorem, that must mean that these two numbers converge to each other. So the squeeze theorem tells us that this integral converges to that integral. That's just a number. That's just a number. By a similar analysis, I can show that this number converges to this number. All I've done here is I've swapped the roles of u and v. Okay? So the analysis is really exactly the same. Now, the next thing I want to do is use the continuity of the trace operators. The trace operator says that, well, if I know that these two functions are both, if I know that let's start with what we know. These two functions are both in H1, right? This is in H1, this is actually in C1. So their difference is in H1. The trace operator tells us that that difference, because it's an H1 function, has a boundary trace. And its boundary trace, we're just going to call, instead of putting that gamma for the trace operator there, we just usually drop the gamma because it's understood the boundary values go by the same name as well. But notice that I'm measuring them now in the norm on the for the function space on the boundary, L2 gamma. Likewise, I know that v minus vn is an H1 function. It has a boundary trace, and I also have this continuity of the boundary trace operator. Now, as n goes to infinity, because un converges, sorry, un converges to u and vn converges to v, these guys go to 0, right? So that means these guys also go to 0. I can prove then the following fact. Using that information, I can show that by essentially the same analysis that we used up here, we're just going to try to squeeze these two integrals together. I can show that this integral converges to that integral. The one thing that's a little bit missing and requires a little extra work is, what about this nj here? What do you do about that? So don't worry about that point just now. But if all of these integrals converge to the right thing, then I can pass the limit. What does it mean to pass the limit? That just means take the limit as n goes to infinity, or each one of these terms. What do you get? Well, you have to precisely get each one of these integrals in exactly the right places. And so that says that because I know that the formula holds for C1, and I know that I have this particular density result, I can show that this formula holds more generally for functions that are rougher, namely functions that are in H1. Okay, so this is an example of my knowledge about something being true for smooth functions can be translated into my knowledge of the same fact for rough functions if I know that I have the appropriate density results. Now, I want to apply this sort of density argument within another context, in the context of the so-called Poincare inequality. Now, Poincare inequality is something that we talk a lot about in 572. Dr. Salgado, when he teaches it, talks about it. I certainly do when I teach 572. So for those of you at the University of Tennessee who've taken that course, you've seen Poincare inequality. I'm going to give you another flavor of that, but I'm also going to show you how to prove it using a density argument. So suppose that omega is an open bounded domain. It doesn't actually have to be a Lipschitz domain. It doesn't have to be all that nice, but it has to be contained in a d-dimensional hypercube with side lengths s. So what I mean here is that I'm talking about a set that has to be contained in a box. Oh, that's not what I wanted. Okay, so the side length has to be well defined. That's S. And so my domain doesn't have to be all that nice, but it just has to fit inside that box. Okay, so omega fits inside that box. Then I can prove a Poincare inequality of the following type. For all v in H01. So I don't know if you remember what H01 is, but H01 is the completion under the H1 norm of these compactly supported C infinity functions. So what I know is that because of that definition, C0 infinity functions are dense in that set. Now, these sets, because of the trace operator, are really like functions that are just they're Sobolev functions that are zero or have zero boundary trace. In other words, they're functions that are zero on their boundaries. Okay? So for such functions, we can prove that the L2 norm of V is less than the H1 seminorm of V. What's the H1 seminorm? You may ask. Let's see. I'm going to clean that up a little bit. What's the H1 seminorm? The H1 seminorm is just that part of the H1 norm which contains the derivative terms and only the derivative terms. Okay? It's the square root of the sum over over alpha, where the order of alpha is exactly equal to 1. So these are all the first partial derivatives of V. You take the L2 norm and square it, sum that up, and that gives you the H1 seminorm. So it's only the highest order derivative parts. We're going to come back to this again and again. So don't worry about memorizing it. So how do I prove this? Well, it turns out I gave you a couple of exercises in the homework to prove the Poincare inequality in one dimension. You may have seen a proof of it in multiple dimensions. So I can give you a hint as to how to prove this for smooth functions. But I may put this on a homework as a homework exercise in the next homework, and we'll see how you do with it. But you should be able to prove this result if you're given the right hint for functions that are smooth. So I'm going to kind of take it as a known result that this is true for smooth functions, as long as we're in C0 infinity. Okay, so if that's true, if this is true already for V in C0 infinity, how can we prove it's true for functions that are in the Sobolev space H01? The answer is we're going to use, again, a density result. And this is kind of clever, so pay attention to how this works. So let's let V be in H01 and let it be any function from that space arbitrarily. There is a sequence Vn in C0 infinity such that Vn converges to V in H1, right? That's what it means to be dense. And actually, this space here was defined as the closure of that space. So this density result is by construction. Okay, so V is what we're starting with. The sequence we conjure out of thin air, but the sequence is a sequence of smooth functions. Here's what we're going to do with that sequence of smooth functions. Take the L2 norm of V, add 0 by adding and subtracting Vn, use the triangle inequality. We're still in the L2 norm here with the triangle inequality here. I forgot to copy it here. All right, now we know that this Poincare inequality, whatever the heck the Poincare inequality means, I'll show you how it's used and what it means in the next class. That's just Poincare inequality for each Vn, right? What about this inequality here? Well, we know that Vn converges to V in H1, so we're just going to travel around with this fact for a minute, okay? Just leave it there for a second. Okay, so all we've done here is applied Poincare. So this is kind of triangle inequality. Let's write that above here. So triangle. Here's our Poincare. What's next? Now in this Poincare, well, in this norm, I'm going to add 0 again by adding and subtracting V. Okay. Then I'm going to use a triangle inequality on the seminorm. It's known that the triangle inequality holds for a seminorm. It's not exactly a norm per se, but it still has the triangle inequality property. Okay, if I apply the triangle inequality property for that, I want to do it in such a way that I get out the H1 seminorm of V. Of course, it has a prefactor of S. And then this term comes along, and then this new term from this difference comes along as well. Okay, so that's what I want. I really want to show this is less than that. But now remember I said that the H1 norm has an L2 norm built into it. It also has the semi-norm built into it. So both of these are less than the H1 norms, okay, of the difference inside. So if I take these guys, then this is less than 1 plus s times the H1 full norm. Now again, I know density is true. I know that Vn converges to V. So there has to be an n. So let's fix epsilon. This is the good old epsilon trick. Let epsilon be as small as you please. There has to be a capital N such that for all little n bigger than capital N, because this is converging, we can say that this is smaller than epsilon over 1 plus s. Well, that means that this whole term is less than epsilon, right? So if I combine this estimate that I got here with what I just learned, then that says that the L2 norm of V is less than S times the H1 semi-norm of V plus epsilon. But epsilon is as small as I please. You can show that if I have an estimate like that, A plus B, sorry, A is less than or equal to B plus epsilon for any epsilon greater than 0, that implies that A has to be less than or equal to B. I encourage you, if you've never seen the proof of that, do the proof of that. But we're done because now we have exactly what we wanted. We have to know that this is true. That is to say 6.3 is true. And that's precisely the Poincare inequality that we wanted to prove. So there's another example of what's called a density result. So next time, we're going to show how all of this machinery that we built up over the last few sections, remember we started off with the model problem talking about what finite element is and what it does. And then we moved on to an abstract setting, and then we said, well, we need to know some information about partial differential equations and estimates and Sobolev spaces. We built up a bunch of machinery. Now that we have that machinery, we're going to go back and start looking again at the finite element method. So with that, I will end the lecture and I can take any questions you guys have.